Okay, so let's look at our simple example. So what I'm going to do in this example is the following. Let me expand this. I'm going to set up a very simple state space model, and then I'm going to fit it to inflation process, PCE inflation process. And the reason I'm going to do it is because it's fun, right? We will see how to implement different components of state space modeling approach, but also we will test whether the feds are doing their job. As we know, Fed has a mandate to control the inflation, right? Inflation and unemployment and full output of the economy. But inflation is an important part, and especially right after the corona virus epidemic in the United States, inflation was very high, and during 22, 23, inflation was so high it became a political issue, right? And we will fit this little model, and we will see whether the feds are doing good job at what they're supposed to do. Obviously, I'm doing it in as almost in jest, right? But it's still an interesting exercise. Okay, so we're going to implement this very simple state space model univariate, right? So this it's basically an autoregressive equation with a constant or with a trend for the state. So we have this unobserved state xt. It's autoregressive phi xt1. You recognize it as AR1 process, and there is a constant, right? So very simple. But then the measurement equation is even simpler, right? So we're saying there is some state and there's some measurement error. That's all. There's only two components to it, right? So hence, this is a special, very simple case of a more generic state space model. So if we go the terminology of the general state space model, you can check. Then we make it very simple. So this whole vector model and so on becomes univariate, and all these matrices become scalars and so on, like gamma is 0, and please check these on your own time, right? Now we will apply this model to fit inflation time series. Why do I think it should fit inflation time series? Well, we're saying the following. Inflation is calculated, and in this case we're going to use something called PCE inflation. It's a data set released by BEA, Bureau of Economic Analysis, through a very rigorous, very complicated process of surveying, of some measurements and so on. It's a very complicated process, and obviously there is some measurement error. But what they're trying to do is they're trying to measure the inflation. So I'm going to posit the following, that what we're observing, YT, is the number which is released by Bureau of Economic Analysis, BEA. And it's intended to measure the inflation xt. However, it does so with some error, nu t. And this error is normal and with some variance. Now, the true inflation, I'm saying, is an autoregressive process. So it is stationary, we're saying. And inflation is a slowly changing series. It's not some kind of a random walk. We hope that this phi is actually less than 1, right? And there's some kind of a constant which will bring us to long-run inflation. So if there was no constant, then as you know from AR1 model, the long-run inflation should have been 0. But we know that's not the case. Why? Because the Fed said so. Feds in 2012, after a long period of sort of being cagey about it, Feds announced in January 2012 that explicitly that they are going to target long-run inflation rate of 2%. So you can look up this article. I'll give you the link, which describes this whole history of Fed deciding to make their inflation target explicit. Before 2012, obviously they have some target, but they never released it. They kept quiet about it, so we could imagine what is it, and economists would guess that it's probably 2%, and a lot of people sort of knew, quote unquote, that is going to be it is 2%, but nevertheless it wasn't explicit, and that's why in our series I'm going to pull well, that's why I know there is a 2% target, and I'm going to fit this model. All right, hopefully the fit will go well, and then I will be able to calculate long-run inflation rate from these parameters of the model. And as you may remember from AR1 model, it is going to be the constant divided by 1 minus autoregressive coefficient. So I hope that this would be consistent with 2%. So that would mean my model is good and feds are doing their job, right? Again, in the text itself, right? So again, I gave you the interpretation, right? So the true inflation is hidden, we do not observe, but we observe noisy version of it, which is printed by BA. But by the way, that's not the only inflation measure, obviously. There is inflation without food, without this, and without that, and there is also this inflation which feds are using is called PCE, sorry, not principal component, PCE inflation, which is consumer expenditure inflation. There is another expenditure, right? There is another inflation which is called CPI, consumer income inflation. So basically there's CPI inflation, there's PCA, there's all kinds of different measures of inflation, and you could actually add them all into this Y to measure this one actual inflation rate which we are looking for, right? But in our case, everything is univariate. Okay, what else? Again, we are trying to estimate the true inflation process, right? So next, we're going to implement this all in Python, and while doing so, we will learn about central concepts in state space modeling. That's filtering and smoothing. And because state space models are used to implement, estimation of all kinds of different models, such as SARIMAX, seasonal, autoregressive, integrated moving average processes with exogenous variables, right? SARIMAX function in stats models of Python actually uses state space model underneath. So it's actually just a wrapper around state space model. Now, because these packages are using state space models underneath, it will be very helpful for us to understand what is filtering and smoothing, because these are very like a central concepts in state space modeling. So before we go and implement the equations and Kalman filter and others in Python, let us prepare the data. So we are going to download the data from FRED service, right? So it's Federal Reserve, St. Louis Federal Reserve's service, right? So we will get the data from here, and we will get the series which are called DPC. Well, it's a long mnemonic, but it will be in the notebook. You can easily find it yourself, right? So this will be personal consumption expenditures based inflation, and it actually is directly inflation. It's not a price index anymore. CPI would be consumer price index, and you can calculate inflation off of it. But this is a PCE already calculated for us, so it's seasonally adjusted already, so we don't have to worry about seasonality, and it's an annual rate, right? So we can close this. Let's get back to our sheep here, right? So we'll get the data using this package called Pandas Data Reader. If you're taking my time series course or machine learning course, you probably use this package already. What it does, it goes directly to FRED service of St. Louis Fed and downloads data from there. Another way would have been doing manually, like you could log on to FRED like I just showed, and then download the series, read them into Python, and so on. So this package makes it very easy. So we got the series, we can plot it to see what's going on here, and we actually see that it's quite noisy, this series. And then let's say if we look at 2012, region, then we see it's probably less noisy than it used to be in the past, but like it was hovering a lot around 2% it seems, but then it went up a lot during coronavirus, or rather after coronavirus, due to I guess economic actions of our government and central bank. A lot of money was printed, right, during corona. So I'm going to cut out all the data prior to 2012 January. As I said, that's the date when Feds announced to the world that they're going to use 2% inflation target. So I'm going to ignore all the data before it. So now we loaded all the data, and then my Y now contains NumPy array with the data, right? So my data set here. Now let's actually get to the meat, right? How exactly state space models are working under the hood. So they're working through something called Kalman filter. Kalman filter is one of the reasons why a state space modeling framework is so popular, right? As a filter, what it does, it estimates this hidden state xt given from all the available data at time t. So everything you know about the world at time t, but not past it, will be used to calculate this or estimate the hidden state t. However, the nice thing about this filter is that it does it recursively, right? So in order to calculate this state at xt, yes, effectively it is using all the data prior and including time t. However, the filter itself recursively does it so that it only needs the data at time t, let's say your observation yt, and the previous estimate of xt, meaning at previous time t. So then you're moving right hand side, so from the past to the future, and at every step you're using your previous estimate of xt, and then just like the new data set. So that way you don't need to process the entire data set every time for every point. You're recursively progressing with your filter in the time, right? So this filter also can be used for fitting, for estimation. Because while you are running the filter, you will be able to get the log likelihood function, which you can then maximize, right? So the Kalman filter is defined in Shumway-Stauffer's text in property 6.1, equation 618 through 624. Please take a look at them. But you will find similar equations in any state space modeling text, so you don't need to use that specific textbook. So I rewrote these equations. I adapted them to our simple model. Simplified it. So instead of using matrices, now we're using scalars and so on. And I'm using the following notation. So when I write x hat, I mean the estimation of the state. And superscript refers to the time, I would say the last time where we collected data on y variable, on a state of the world. And t is time to which we are estimating this state, right? So the information set is going to be all the information prior or including time s, but not further, right? So obviously this is the prediction, right? So it's a prediction because it's not using data from the future. And the other thing we would be so in Kalman filter we will be estimating this hidden state, but we're also interested in the variance of this hidden state, and we will mark it at sigma square st with the same indices. So this is a variance. You can see that we look at our estimate minus the true state, which is not observable, so we're looking at this variance. Now when we produce these estimates with s lesser than t, right, so meaning we're using information from the past to predict in the future, is called forecasting. When s equals t, meaning we're using all the information including the time t to estimate for time t, it's called filtering. Now, finally, if we're using s greater than t, meaning we can use data from the future, quote unquote, then it's called smoothing. So imagine you have the full data set and you want an estimate of the state somewhere in the middle of it. If you are allowed to do it, then you're smoothing. If you're not allowed to use any data after that time t, then it's again filtering or forecasting. So Kalman filter consists of two parts again. It's a set of forecasting equations, two forecasting equations. And in forecasting equations, we are forecasting the hidden state, right? So we're using the data from the past to estimate our state at time t. So in this case, for instance, it's t minus 1, so from the previous period, like that would be one step ahead. But potentially when we're forecasting, this may be multiple steps ahead. So how do we progress? It's very simple, right? So if we look at the equation, our state space model, our simple state space model, it looks like this, right? I remember. It's some kind of an autoregressive model. So all we're doing now is basically advancing it forward. We're not using error here. We're just like using the constant and phi, and that's our new state, right? That's exactly what we've done here. Very simple. So our forecasting is simply advancing our autoregressive process forward. Now, how do we calculate the variance? So this looks a little complicated, but I'll explain. It actually is not that difficult. So what we're doing here is we get this phi, assuming we know phi, right? And multiply it by the previous estimate of the variance, and multiply it by phi again, and plus this parameter called sigma square, variance of the errors. Because the variances are not correlated, we can add them. The variance of the x state is not correlated with the variance of the measurement. So we can because it's an independent series, the errors are independent. We can add the variances, right? So the equation looks like this. So to bootstrap, to make the very first prediction, right, at time t0 when our data set starts, we need to guess initial values of t0 minus 1, t0 minus 1. So imagine if our time starts at 0, then we need, or let's say your time is 1, then you need x at 0, 0, very first guesses. And these guesses, only these two guesses we need in the very beginning here, right? And then after that, it just recursively keeps going because we will be using the previous values. So that is our forecasting equations. Now, in my Python code, notice my t0 is 0. So in Python, indexing starts from 0. And I'm using that advantage for convenience. In some other languages like R, indexing starts from 1. So t0 would have been 1. Okay, so like in the textbook, Shopway Stoffer, they're using t0 equal 1. So their indexing starts at 1. And that's why they're saying for your initial values are x0 and x0. So basically you're forecasting, not forecasting, but you're guessing what is your inflation at the very beginning of your data set. And what is the variance of the inflation. So you put the guess and then you run a filter forward. So that is your forecasting equations. Now, there is the second set of equations in the same Kalman filter, and it's called filtering equations. Remember how I said that when we're using the data from the past to forecast forward the state, that was called forecasting. That's why forecasting equations. But I said filtering is when we can use the current data to estimate the current state. And to do that, we need 5 equations. So the set is called filtering equations, and it's 5 of them. So the first equation is something called Kalman gain, KT. And there's some kind of a formula. It looks complicated, but actually derivation is not that difficult. So I won't go in there because we're not doing derivation at the moment. But what's going on here is the following. So this variance of the measurement error is a parameter of the model. It's one of the parameters of the model. We assume that we know it at the moment. But look at this. This is an estimate of the variance of the state, right? That comes from here, from our forecasting equations. However, this was forecasting variance, and we put this into KT, and then we will be able to get the variance for the filter. We'll see that. So anyhow, these all the inputs into Kalman gain are known at this point, right? So we calculated the variance, and sigma square nu variance is a parameter. So that's how we calculate gain. Then we can calculate the prediction error. What is the prediction error? That is, finally, we're using the current observation. We're using YT. It's a current observation for time t. And we're subtracting our estimate of state t for the same period t, but using the past data, right? So it is this xt. So that is our estimate of the error, of the measurement error. So we estimated the measurement error, and now we want to estimate the variance of the measurement error. And it happens so, again, we're using the parameter of the variance error, parameter of the model, but we're updating it with the variance of the state. So you see, we're adding them, and again, because they are independent, we are able to add them. So we add them, and we get the not the forecast, not the estimate, but sorry, not the forecast, but the estimate of the error, of the sigma, of the variance of an error, right? Now, finally, we get to hidden state. So we already forecast or predicted hidden state and its variance. Now we're going to actually apply filtering. So the filtering goes like this. This was a prediction for time t based on all data. And now we are getting TT, right? So we're using current data to get the update. How is it going on? Look, we're using Kalman gain and multiplying by measurement error, which we estimated using the current data. So this XTT is actually using the current data already. And its variance also is using the current data. You see, it's 1 minus Kalman gain, but then we would be multiplying it. Oh, wait a second. It is not, variance is not using current error. Yes, it will use later, but the state does, right? So here we have this previous estimate of or a forecast of the state variance, and then we get the new estimate using the Kalman gain here. Okay, good. So okay, there's 5 equations here, and then 2 equations in the forecasting. It seems in total 7 equations. So we have to implement those 7 equations in the Python code. But before we do it, I want to talk about fitting, right? So here, to run the filter, we needed to know these parameters of the model. You know, all these phi's, you know, phi and this variance of the measurement error. So these are all parameters of the model. So to run the filter, you need to know them, or at least assume them. So that's where maximum likelihood estimation fitting comes to, because how are we going to estimate those parameters? This is how. Kalman filter includes this one more equation here. That is the log likelihood, or likelihood. So in this case, I define it as a negative log likelihood. Why negative log likelihood? Well, because we can minimize it. We are maximizing the likelihood, which is the same as minimizing the log likelihood, or minimizing the likelihood function. So the likelihood function looks like this. You see what are the inputs into it, right? Estimated error and estimated the variance of the error given a set of parameters. So now think of this, how we maximize the likelihood. We assume set of parameters, right? Like this variance of nu, like phi's and so on. These are all parameters. We will assume them. We'll make a guess. And then in the Kalman filter itself, we will be able to calculate likelihood. And then using this minimization tool sets, we will start getting new iterations of the parameter set. We'll get a new set of parameters, look at the likelihood, and so on. And then we'll keep getting trying new set of parameters until we reach the minimum of log likelihood. And that would be the optimal set of parameters. So I described it here, but it's basically similar to any maximum likelihood estimation examples you have seen before, right? So once you have likelihood function and you have parameters, you just try different sets of parameters to get this likelihood maximized or negative log likelihood minimized. Okay. Right, so now we're going to implement this example as a filter function. So in the next two cells, I'm going to implement this whole thing. So I'll implement the Kalman filter, its first 7 equations, forecasting equations, and then filtering equations. And also when filter is done running, it will be returning me, it will be calculating me neg log likelihood. Okay, so that is here. So here I'm using this parameter set, I call it theta, with 4 parameters in it. Our constant, autoregressive coefficient, variance of the state errors or state innovations, and variance of the measurement errors. That's all I need for my simple model. Then I have 2 other parameters, but these will not be optimized. I just set them at once because it actually doesn't matter. You can try, you can play with this code and change my guesses. My guesses for inflation at the very beginning of the data set and its variance at the very beginning data set. So basically, I'm guessing the distribution, probability distribution of the inflation, this hidden inflation, which I'm trying to measure at the beginning of the data set. And again, I'm not changing this. I'm only optimizing 4 other parameters. So walk through this code. I guess I won't do it line by line, but I explain the general idea. So we have this filter function, and we supply the parameters. This filter function is not written very well in terms of like Python coding style. So the coding style is not good here because it is using external or global variables. So normally when you code Python, you shouldn't be doing that. But I'm doing it here because I don't really care for the notebook. I'm just like trying to I'm not teaching you Python here, right? I'm teaching you how to implement filter, Kalman filter. When you implement your own Kalman filters, please don't do this, right? So do not use global variables, but my filter does. So my filter gets the parameters and parses the 4 of them. So my parameter vector will contain 6 parameters, but only 4 of them are used to optimization. So these 4 will be extracted here. And these are epsilon, phi, and variance of parameter, which is a variance of state and variance of the errors of the observation. So I'll be changing these 4 parameters from outside later. But anyhow, when I'm given the parameters, I am able to calculate my Kalman filter. How do I do it? I'll run my Kalman filter through time t. What is t? T is my data set. So it starts at the beginning of the data set, let's say in 2012, and then goes all the way to 2014 quarter 1. So it starts from T0, 1, 2, 3, 4, and so on. And as we know in Python, as I said, indexing is from 0. That's why I'm using this range function. So I'm running through all my Y data set. I'll run through this data set, and then I'm simply calculating these equations one by one. And I gave the number references of equations so that if you're reading Shumway and Stauffer's textbook, you can easily find them in the textbook, right? So this is my forecasting equations for my state and its variance. These are my forecasting equations. And then we'll start with filtering, right? So this is the error estimate and its variance. Measurement error, right? And its variance. This is a Kalman gain. And these two are filtered state and its variance. So I'm using these P and X as from the textbook. But this is the variance. And then what? And then I store this as previous values and then go back to my loop and then start again. Calculate the next step of my filter. And that's the reason why we're saying we're only using this Y in one place. Right? So it's a filter, it's a recursive filter, it's based on the previous values. So we'll keep doing it, and while we're doing it, we calculate the neg log likelihood. Very simple implementation, right? So you have these epsilons divided by sigma, and there's some kind of a log and so on. Simple implementation of the formula. and then we will return neg likelihood. We divide it by 2 here, because this formula is double no, log likelihood, so we divide it by 2. Okay, and there's little test to just to run and see that the method works. Now the next is going to be a maximum likelihood estimation using this Kalman filter, right? As I said, the filter equation itself, function itself, returns log likelihood.